Hey Phys 2 kids, Campbell here. In your second video for your summer assignment, we're going to talk about pressure in gases, forces, and something, if you've taken chemistry, you know about, the ideal gas law. So remember we said that in our last video, kinetic molecular theory talks about how gases are in constant random motion, that their kinetic energy is proportional to their temperature, that they don't lose energy in collisions, and we focused mostly that video on internal energy and temperature. Well, there are 4 thermodynamic states of a gas that are all very important to the behavior of the gas. We've talked about the absolute temperature, Kelvin. Today we're going to talk about pressure and how pressure is caused in a gas, as well as some things that affect pressure like volume, matter, temperature, those things. So let's talk about this pressure that gases create. So gases create pressure because they're constantly moving around. They're bumping off each other on the walls of the container, and every time they bump against the wall of the container, anytime we have a collision, we're going to create an impulsive force, right? And the faster we're moving, the bigger that impulsive force is, right? If you run into something when you're running fast, it hurts a little more than if you're going slow. So we call that an impulsive force. Now, the equation for pressure, and by the way, we don't use a little lowercase p, it's always an uppercase P, is the amount of force in newtons over area meters squared. The SI unit for pressure is the Pascal, which is a newton over meter squared, obviously. This is the SI unit. It's not atmospheres, although you can transfer atmospheres into pascals using the conversion factor of 101/300, which you can find on your equation sheet. Now, what this means is the only way to have zero pressure is to have zero molecules, right? Because then there's nothing to bounce off the walls. But could you imagine trying to remove every single molecule from a container? It's not very easy. In fact, it's almost impossible. So to get a perfect vacuum of 0 pascals, it's not really easy to do. So what is this impulsive force, and how does it actually relate to the ideal gas law, right? The ideal gas law is PV equals nRT. Where does that come from? Well, it actually comes from impulse momentum theorem. So here we have a molecule in a box, and it collides with the walls of a container. So there's maybe an initial velocity, and then it's going to bounce off, right? So impulse causes a change in that momentum. And remember that if the collision is elastic, then that final velocity is equal to the opposite of the initial velocity, right? Velocity is a vector, momentum is a vector. So, and we just recently on the last slide said that pressure is equal to force over area. So if we rearrange this equation here, we can, instead of force, we'll put in our pressure times area times delta T is equal to, now the mass isn't changing, right? It's the velocity direction that's changing, because remember it's elastic, so there's no actual magnitude in change. So if we did this as I have it pictured, right, that would be V final, right? It's always final minus initial. Oops, sorry about that little dagger. Minus the initial, right? Which, if these are equal, means that we have our pressure times our area times delta T is equal to M times 2V. The velocity of a molecule in the container. And of course, there's lots of molecules, so we would multiply that by the number of molecules. But how do I relate this to this equation that we're going to talk about in a second, the ideal gas law? Well, if molecules are moving, right, we have a velocity, which would be the change in position over change in time. And our position, right, would be like, across the box. That could maybe be our x. Period of time. So if I rearrange this for time, right, we get x over v. So I'm going to plug that in over here because there's no time in an ideal gas law equation. So we got our x over v, and that's equal to 2mv. Look at this. Area, right, area times, well, maybe I shouldn't have picked that area. How about this area? Area, which is what I'm colliding with, right? The sides are what I'm colliding with in my little picture, times x, right? That's volume. So we have pressure, volume, and I'm going to move this v over here, right? And we get 2mv squared. It's kind of like kinetic energy, right? Kinetic energy is 1/2 mv squared, which we know from our last video is equal to 3/2 Boltzmann's constant, T. Oh, I'm going to get time in there. So I can replace this with this, and I got PV is equal to 2 times 3 kBT, and the stuff is moving in 3 dimensions, so there's other fun stuff that goes on with this. And this is for one molecule, right? But then I got to multiply by all of the molecules that I have, and I come up with the ideal gas law. The ideal gas law relates all the quantities, all these thermodynamic quantities of a gas together. P times V is equal to N being the number of molecules times Boltzmann's constant times temperature, again, in Kelvin. Pressure has got to be in pascals, volume's got to be in meters cubed when we do this. Now, you may not have seen the ideal gas law in this form if you've taken chemistry. But remember that number of molecules times Kb is equal to number of moles times R. So we can also write the ideal gas law as our Pvnert, PV equals nRT. Again, in physics, we're very specific about our units. Pressures in pascals, volumes in meters cubed. By the way, there are 1,000 liters in 1 meter cubed. You might want to write that down because that conversion factor is very important, because we typically talk about volume of gases and liquids and stuff in terms of liters. Our gas constant for these quantities is 8.31. Our temperature in Kelvin temperature is always in Kelvin. All right. Now, what this means is that if we change any of these properties, that volume, temperature, we're going to change the pressure, because if we increase the frequency of the collisions or the power of the collision, then we have more collisions and more powerful collisions. And so one of the things you can see from looking at the ideal gas law is that pressure is proportional to temperature. If temperature goes up, pressure goes up, right? If I increase temperature, I increase speed, which means they're going to collide faster. I'm going to be hitting those walls more often. I'm also going to be hitting them with more force. Pressure is inversely proportional to volume. So for example, if I had like a bottle, that squeezable bottle that I just had filled with gas, if I squeeze that bottle, if I decrease the volume, pressure goes up. So volume goes down, pressure goes up. Finally, molecules, right? This makes sense. The more molecules I add, the more pressure, right? More collisions, more pressure. So anything I can do that will increase how many collisions are happening per second, or how fast impactful those collisions are going to increase pressure. And we can see that from using our ideal gas law. Now, since PV over NT is equal to this constant, the gas constant, that means that the pressure, volume, amount, and temperature at one condition has to equal the pressure, volume, and amount and temperature at another condition, right? So we could set these two things equal to each other and get rid of that ideal gas law completely, and we get this. And any factor then that remains constant when we're doing some calculations, right, just divides out. So we get rid of the amount and we have the combined gas law. We get rid of the amount and temperature and we have Boyle's law. Or we could get rid of volume and we have pressure over temperature, which is Gay-Lussac's law, or we could have Charles' law, or we could do Avogadro's law. But because these things have to stay constant, I can use the ideal gas law to look at equalities between different conditions. So let's ask some questions. I have two identical cylinders, A and B, and they contain the same type of gas that are at the same pressure. Cylinder A has twice as much gas as cylinder B. So what must be true about the temperature? Pause the video and see if you can figure this out. Well, because volume and pressure were the same, then we have an inverse relationship between the gas and the temperature, right? If we're going to add twice as much amount, right, then we have to decrease the temperature. So the temperature in A has to be less than the temperature at B for the pressure and volume to remain constant. All right, let's try another one. I have my two cylinders A and B again, and they have the same type of gas. This time they're at the same temperature. Cylinder A has twice the volume of cylinder B, but contains half as many molecules as cylinder B. So what's true about the pressure? Pause the video, see if you can get it right. Well, if we rearrange our equation to solve for pressure, right, we have molecules on top and volume on the bottom. So that means that instead of these things working against each other, they add together, or they work together or multiply together. So if I have twice the volume and half as many molecules, I'm going to have a quarter of the pressure in A as I do in B. All right, let's do some math. I want to know about the final temperature of this gas if in my initial conditions I have 1.5 meters cubed volume of a gas at 27 degrees Celsius when it's under a pressure of 0.2 times 10 to the 5th pascals. And then I'm going to squeeze the gas till the volume decreases to 0.7 meters cubed and the pressure has gone up to 0.8 times 10 to the 5th pascals. Now, I want the temperature in Celsius, but you cannot work in Celsius when you do this problem. So make sure you convert to Kelvin first. Pause the video, see if you get it right. Well, in this problem, we can just use the combined gas law, right? Pressure, volume over temperature in one condition has to equal pressure, volume, and temperature at the other condition. Again, you have to work in Kelvin, so make sure that you add 273 to that 27 degrees before you do your math, or you're not going to get this right. Now, when we set it up and solve, you should have gotten a Kelvin temperature of 560. But I wanted it in Celsius, so now you got to subtract the 273, and you'll get 287 degrees Celsius. Now, for those of you who didn't convert to Kelvin, you did not get the right answer. And if you don't believe me, because you think I just want you to do extra work, try it and see. All right, one more. I have 2 moles of an ideal gas in a 5-liter vessel at a pressure of 8 times 10 to the 5th pascals, and I want to know what the average kinetic energy of a single gas molecule is. The kinetic energy? What? Oh. Pause the video, see if you can figure out how to solve this. Well, hopefully you remembered that the average kinetic energy of a single gas molecule is related to the temperature of the gas. So we need to use the ideal gas law to find out what the temperature is, and then we can use our kinetic energy equation. So we got to do a little PV equals nRT here. We have moles, we have a pressure in pascals, but notice that the liters, the volume unit is liters, and we need meter cubed. So make sure that you remember there are 1,000 liters per meter cubed. So to calculate the temperature of the gas, right, just plug in your variables, make sure they're in the right units. You should get 241 Kelvin. Now we got to plug that into our average kinetic energy equation. Now in this case, I only asked for the average kinetic energy of a single gas molecule. So you don't have to worry about multiplying by the amount of moles or the number of molecules. So we can just use the equation that says the average kinetic energy of a gas molecule is 3/2 kb times T. So we plug that in to our equation, and you should have gotten about 5 times 10 to the negative 21st joules. How'd you do? All right, now that you're done with video 2, it's time to go in Canvas down below to the Google form, answer the summary questions, give me a question if you've got one, and answer the calculations. Well, they're not really calculations, are they? Well, maybe. I don't know. And don't forget, there's an assignment. This assignment number 2, you should have done the first one already. Assignment number 2, again, this packet is due on the first day of class. So get to work. See you in class.